There are several reasons to give a talk. One is that you've done something you're very excited about and you want to tell your friends. Another is that you want to tell your friends because you're trying to get converts or insights. We're somewhere in between. What we're working on these days is a new kind of coherence effect, many particle, superradiant-like physics, but looking at the holy grail of generating high-frequency radiation, maybe XUV, with the coherence techniques that we've been looking at vis-a-vis lazing without inversion. Okay, but it's not the same. And so I'd like to start off by motivating what we're doing and try to get your curiosity with me before I tell you of our results. By the way, how many of you know phys rev X? I didn't. I thought, A, B, C, X, right? So do you guys know phys rev X?
Sure. Yes.
Yeah. What does X stand for?
Exactly. X-Files. Exception.
It stands for extra hassle. So we sent this thing into phys rev X, this superradiance amplification effect. We got 3 referees. They all said publish, but one of them said, but I really don't understand how this is different from ordinary parametric coherent scattering. So you got to explain that. So we really went back and explained that carefully. We put in oscillator models and stuff and did little experiments in the electronics lab, sent it back in. They said, oh, now you have a little experiment. 3 more referees. Those 3 all said publish. This is great. Went back to the first 3, and the guy who didn't understand it says, now I really don't understand it. So you should send it to phys rev A. So at this point, 7 referees into the game, we complained to the editorial board, and they said, oh, yeah, go ahead, publish it. So in order to avoid some of that problem, let me tell you how we got here and why what we're doing is something that seems intuitively reasonable. So we start with Dickey Superradiance. So you tell people, I have a complex of atoms in a diameter small compared to the wavelength. And if I go with Dickey, we line up the atoms in a coherent fashion. And so in the first column, think just the single photon excitation of a coherent ensemble of atoms in which the wavelength is, as Dickey was thinking, say radio frequency, very large compared to the size of the sample. So R is very small compared to lambda. And the Dickey picture then concentrates on breaking things down into a first column, which is a permanent. And he says, well, think psi for 1 photon excitation, okay? He says, well, that's equal to our notation, upper state A, lower state B. This is now a configuration in which I could have had the first atom excited, and all the rest of them are in the ground state, n of them in my volume, plus, and so on, up to the jth atom excited, and all the rest in the ground state, and finally, the nth atom is excited. Okay, so this is in a sense the simplest Dickey state, normalized to 1 over the square root of n, but also the most quantum mechanical. By that I mean, if I ask myself, what do I expect the radiation rate to be from this configuration down, I might say, well, look, it's just gamma, because it's single photon physics. But of course, it's not. If this is gamma, then this rate, let's call it capital gamma sub n, is equal to n times gamma. That's Dickey 1954. And by the way, in the conference proceedings associated with Dickey's historical paper, people were always saying, oh, Dickey superradiance is nothing very interesting because it's just the dipoles lined up radiating in a coherent fashion. nuclear magnetic resonance, Bloch equations. Dickey pointed out, yeah, well, think about this state. It's certainly not the case that you can explain the enhanced decay rate here without quantum mechanics, and that's right. Okay, so march on, quarter of a century. Around 2005, we were talking to Steve Harris about some of these coherence effects, and he asked an interesting question having to do with a large sample, and asked, can you have phase matching at the single photon level? So we found that this was equivalent to the question. Now, so this is 1955, Dickey. So 50 years later, 2005, we're asking the question, suppose I have a sample which is large compared to the wavelength, and suppose that I excite that sample in some experimentally feasible way such that all I'm doing now is putting in the dipole factors e to the I k0, wave vector of excitation k0, dot r1 and so forth up to here, e to the I k0 dot rj, and so forth. So these phase factors are essentially timing factors. They're telling us that if I turn this into a frequency times a time, these factors say that the atoms on the first edge of the sample are excited first, and the last edge are excited last. So there's a kind of coherent phasing of this kind of what I call timed Dickey state. So we sent that in to PhysRev Letters. It got published, no problem. And then we said, well, what, oh, sorry, very important to tell that this distance is something which is small compared to the wave packet of the emitted photons. So that let's note that here we're talking about a radius which is large compared to the wavelength, 10,000 wavelengths, say, but small compared to the speed of light divided by the typical decay times. Okay, so the atoms are all seeing each other through the vehicle of this wave. Fair enough. Then you ask, what if, and this is the key point, what if I expand this to an even bigger sample such that I relax this limit? Okay, so now the photon wave packet is here. So let me try to indicate that the wave packet of the radiation is covering the entire ensemble. So now you think, well, what if I make a bigger system of atoms? And you might think, well, it might not be very interesting, but it turns out to be very interesting. Same state, but now with this caveat. Okay, now what you find is a surprising result. Let me ask, what's the probability that I have one photon in the cavity? Cavity? No cavity. Cloud. One photon in the cloud. I started off with no photons, only one excited atom in this kind of complex. I didn't know which one, but I had an excited atom. Now, same thing, do the calculation. Here's what you get. You find that this goes like sine squared, matrix element, dipole matrix element, between the two levels over h bar, times something which is almost intuitive, h bar times the frequency of the incident light, divided by epsilon 0, because we're in practical units, times the volume of the cloud, times the square root of the number of atoms, times the volume of the cloud, times the time. Right away, I say to myself, hey, look at single photon cavity QED. Please to remember that if I put one atom in a cavity, and I ask, what's the probability that I have, in some sense, excited that atom where I have, let's say, little n photons. So I'm going to put the atom in the ground state, put little n photons here. Here I have only one photon physics, but many atoms. One photon, n atoms. Here I have one atom and many photons. Okay, everybody knows the answer here, so now I'm asking for the probability that the atom is excited. Okay, I certainly know the answer to that one. Sine squared matrix element over h bar times the square root of the electric field per photon, which is the energy per photon, h bar nu, over epsilon 0 v cavity times the square root of the number of photons times the time. So I look at these two and I say, oh, this is very interesting, because here it's the volume of the cloud that counts and the number of atoms, and in some kind of interestingly symmetric way, here it's the volume of the cavity and the number of photons. Fair enough. And you go back and look at this calculation over and over again, and you find that this factor is really a ubiquitous coherence factor. We call it omega sub A. The reason for the notation we'll discuss in a minute, but the point is that I'm seeing a kind of plasma effect, a kind of collective effect. It's going like the square root of the number of atoms. That's the hallmark of a plasma oscillation, right? It goes like the square root of the number of electrons. So here what we're saying is that the coherence of this atomic ensemble is giving us an interesting kind of modulation of the excitation. So if I plot P of exciting, so I'm first of all exciting the photon oscillator here as I tell the story, and here I'm exciting the atomic system, the one atom atomic system. So it's giving me something which is ringing at a period which is not the Rabi frequency, but this collective frequency. So this period is a many-atom collective frequency in the superradiant case, but it's a Rabi frequency, single photon Rabi frequency, times the square root of the number of photons in the atomic case, cavity QED, cloud QED. Superradiance, coherence, many-atom coherence, no real coherence here in the sense that I have only one atom driven by a photon beam, so the coherence is not very important. Well, right away you say to yourself, hey, the basis for the Walter-Hirosh experiments is this, and it's also the basis for all of laser physics, right? Stimulated emission. And I know that I can make a laser field by just exciting these atoms at the right time using this kind of insight. How about this? Could I maybe take an ensemble of atoms like this, and this is PRL now 2007, and could we perhaps make an interesting new kind of source of radiation with the coherence, many atom coherence coming in, motivated by this type of idea? Okay, so that's the setup. And now let me walk you back to the 1970s. Down the street at MIT, we had a really great quantum optics group. And great quantum optics group here. We had Roy Glauber up here and lots of interesting people. Bloomberg down there. We had Towns and Javon. We had two guys you haven't heard of as much, Dave Burnham and Ray Chow. Chow went with Towns to Berkeley when Towns left after not being provost at MIT, a real loss to MIT. And they, Burnham and Chow, had seen this kind of physics, and they called it coherent ringing. And they were always thinking about this collective square root of n plasma type effect. Oh, interesting. And I'll tell you more about that in a minute. But it's always been in the back of my mind that there should be some way to see superradiant effects on the one hand and single atom coherence effects on the other. And that is, of course, a story that we'll just allude to. But this is the motivation. And now let me say, punchline. We find that in principle, the equations tell us we should be able to send in infrared light, all the atoms in the ground state, and get ultraviolet X-ray photons out with fairly high efficiency, surprisingly high efficiency, okay? High enough efficiency, it'll get you forbidden from phys-rev X. Which, by the way, phys-rev X sounds like a great idea because it's phys-rev letters with no page limit. So, now let me start into this talk, hopefully. Somehow, do I put this down?
Do you want to use
Oh,
the
could I?
remote? Yes.
Oh, no, I'll just use this.
So
But if I had a,
You'll just
good,
press the things.
good. Oh, a green pointer, wow. I don't need any view graphs, I got a green pointer.
Let me turn off the wireless so that my mom doesn't call you.
Maybe she has a question. While I'm waiting for this to come up again, there's a really great young student, Luji Wang, who is the guy who's done many of the calculations here, maybe even most of the calculations, a bright young kid who's just coming out. The abstract says that lasers and masers, population inversion, phase coherent, lazing without inversion, but you still have to have atoms in the excited state, maybe 10%. There are other constraints to lazing without inversion having to do with decay rates that make the whole process pretty hard in steady state. But if you start looking at time-dependent lazing without inversion, then things are different. And now we find that it's possible to get coherent light with no atoms excited via quantum amplification, of which lazing without inversion is one example, but now using superradiant emission, not stimulated emission, in a very specific and practical sense that I'll tell you about. So, of course, we all know that single atom quantum coherence effects are associated with off-diagonal elements of the density matrix. The first application of this in lasers was in quieting spontaneous emission noise, and that was observed by Hall and Toshak. And the lazing without inversion gambit then came on the scene such that the coherence between two levels in a lambda configuration give us the possibility of lazing with, say, 10% of the atoms here, 90% there. Let me go back. We had some really great times in the old days, wonderful calculations, guys like Lukin and Nikonov pushing forward, and experimentalists like George Welch. We showed this at a conference, and Steve Harris looked at it and he said, I don't want to see any more theory, I want to see experiments. This was such a beautiful experiment that it certainly looks like theory, and the theory agrees very well. German Süddeutscher Zeitung touted this as striking against the dogmas of physics. But now comes the present story. I read something like this abstract earlier, so I'll now tell you in not too much detail, I hope. So I have another hour and a half. What time are we?
Let's see. Supposedly 12:10, and it's but you started late, so 12. I'd say 12:15.
Sure.
So you have about,
Good. I'd do anything you say. Now, please to remember this parameter that I called omega A. So this goes like the omega A goes like the square root of the number of atoms. So omega A squared is something which is proportional to the number of atoms. Omega is the Rabi frequency for the transition between A and B. So this is ultraviolet light. The wave equation over here, omega AB, is the frequency, say, ultraviolet. Think hydrogen. So this is maybe 100 nanometers, some such. And what else do I need to define? Rho AB is the off-diagonal element of the density matrix. So we write the coupled Maxwell-Schrödinger equations, where, again, this is the Rabi frequency of the transition we're trying to generate light on, and it's also going to become a Rabi frequency for another infrared signal, the population of the ground state minus the excited state. So this is laser physics, this is superradiance, but I remind myself that that omega A is a coherence effect under the right conditions, many particle coherence effect. So let's look at what you get when you put those two equations into the computer and propagate through a long tube of atoms. Let's put a drive on which is infrared, and let's ask for what would happen if I'm looking for 3-photon excitation from A to B, always thinking about something simple like hydrogen 2p to 1s. So you send in the infrared drive pulse, and you look in the forward direction, and so the input pulse is here, the forward direction, you don't really get very much, and we haven't really tried hard, but that's what you get. Now, look in the backward direction. Here's the input pulse. In the backward direction, you see a very strong pulse. You see very strong emission. And we can argue physically why you might think that would be the case. It's a lot like Raman backscattering. But the physics is simply that as I put in the drive and I look at the UV building up from vacuum, the UV will be, which I call omega laser here, or omega superradiant, will be counter to the direction of propagation of the drive. And I say again, this is completely computer simulation. There are no approximations. We didn't even make the rotating wave approximation. We don't have to, but we do keep everything. We go back and do this analytically, and we find, again, that there's a strong gain in the backward direction, and now comes the reason for the referee's comments, angst. Think multiphoton physics, think Ron Chen's book or Bob Boyd's book, and if you look at the conversion of infrared to ultraviolet, you say, what's the probability of excitation from the ground state to the excited state? So for M absorbed photons, here M is 3, I have the ratio of the drive Rabi frequency to the atomic frequency raised to the 2m power times omega ABT. So this is just every textbook result, and it's intuitively quite reasonable. This is a small number, very small number for most experiments, but not so small for experiments that we're doing now both at Princeton and at Texas A&M. Okay, this is the old stuff. Here's the result of calculating the probability of excitation under these kinds of collective effects. What do you mean collective effects? I mean the superradiance kind of analog in which each atom is excited a little bit and there's an overall coherence between atoms. Now we calculate the probability of excitation, and it goes like the incident pulse squared, and that's related to a little bit of coherence on A and B. Not very important. What's important is that now we have an exponential of omega d squared over omega AB squared times the collective frequency times t. This is a very manageable number. This is a teeny-weeny number for any experiment that you might think of using these ideas. This might be 10 to the minus 20, whereas this might be 10 to the minus 4. So it's very interesting that we're getting extremely efficient, in principle, according to computer simulation and analytical calculation, we're getting extremely efficient excitation and generation of light.
Marlan, the argument of the exponent is 10 to the minus 4, or the whole thing is 10 to the minus 4?
So this upstairs might be something like omega d, take that to be, say, 10 to the 13 in our experiments. And omega AB maybe is 10 to the 15. So this is 10, something like, 10 to the minus 4. But this omega A, hey, that's a big number. These numbers are like 10 to the 16, 10 to the 17 for a density of a few torr. Okay, well then you got the time coming in, which is femtosecond. So lump it all together, and you can actually get gain here. This is gain. You can actually get these numbers on the order of 10. But if I just look at this ratio compared to that ratio, that's what I was saying. This is 10 to the minus 40. This is 10 to the minus 4. So you and I don't care about factors of 10 much, but in the exponent they matter.
Sorry, I have a very stupid question. I'm sorry, I'm sure you said that at least 5 times, but I still didn't quite get where the backward direction comes in.
Yeah, how come backward? What, so you're telling me you get efficient excitation. Why is it in the backward direction? It's because what's happening is we're modulating the coupling between the field and the atoms. And so this modulation, as in the case of, for example, the free electron laser, always gives you maximum gain in the backward direction. The free electron laser, okay, I'm setting up this excitation, this ripple associated with one wave coming in, and I'm backscattering off of it. That's one example. Another example is backward Raman scattering. Backward, here's my expert, backward Raman scattering. So first thing I see this, I say, hey, I got to go get my friends down the street, but he's gone now, right?
From where? Yeah, here.
Yeah.
He's not down the street.
He's never down the street.
Well, Marlan, I have a much simpler question. So,
But I missed my point, right? He says, oh yeah, this is a lot like backward Raman amplification, right? You say that.
I didn't say anything, but
Go ahead.
I have an even simpler question. So presumably you will have lower frequency transitions as well. So can you make sure that your drive is not going to be wiped out by what you call traditional parametric amplification?
Okay, so, yeah, but there are three ways to approach this. First is the simulation. Okay, let's just do the numerical simulation.
But does it include all
Okay.
levels or all of
We'll put in those extra levels, and we can do that. We've got a super computer jock, this guy Lucci. Then we'll do the analytical calculations, and then we'll start giving you examples of laboratory situations in which this effect comes about. And that's the real killer. That's the real convincer. It turns out that this is something which is not like parametric oscillation. Parametric oscillation is some frequency generation. What we're doing is so-called difference frequency generation. And we're coming there.
I'm not saying that it's the same thing. I'm saying that
And we've done an experiment, and we see the effect.
I'm saying that
How you like that?
amplification could be kind of the spoiler, right? Because it will affect
You could say the amplification is going to be washed out by all these other effects.
your drive will basically
Could
be
be.
depleted by parametric
So
traditional
the thing I'd
parametric
really like to tell you is, thank you, we've done the experiment and we see the effect. And I'm 90% of the way there. We've got experiments going at Texas A&M and Princeton, and we see these effects. I tell you in private as a friend. Right?
So we are not your friend, Marlan?
Huh?
We're not your friends?
Oh yeah, all of you are my friends. I got to tell you a story. So a decade ago, I found out how to detect anthrax. So I got the money from DARPA, and I went back home, and I found out that it was going to cost me more than that amount of money to get the femtosecond lasers. So I went to Michigan. So you do the experiments. Here's $1 million. They said, no, it's not going to work. So I went to Princeton, and they, Warren and crew, had these nice femtosecond lasers. And so I'm explaining how we want to do these coherent cars effects. And some guy raises his hand in the back of the room, and he says, you're wrong, this is stupid, it won't work, and here's why. And so I don't want to fight with this guy. I want him to do the experiments, right? So I say my favorite line, look, I like my strongest criticism from my friends in private, not my enemies in public. And he says, wait a minute, I count 200 people here, and we're not your friends. So we argued, and finally they did do the experiment, and we did see the effects, and it's not that different from what's going on here, because this is a kind of coherent Raman sort of thing. But how do I understand it? What's the simplest way to try to get this physics wrestled to the ground? So I started doing these calculations using a kind of canonical transformation, and since my time is either up or almost up, I got 5 more minutes?
Yeah.
So let me just take the remaining 5 to tell you that Gibson from UConn did a very interesting calculation many years ago and reported it at the Physics of Quantum Electronics School, in which he pointed out that if in addition to 3-photon drive, you have a off-resonant, same frequency, infrared, coupling 2 excited states, you can get a real enhancement of the excitation due to this kind of counterintuitive effect. So I love this stuff, went through the calculation, put it on the computer, that is to say, went to Lucci and he put it on the computer, and we find now that we start with our ensemble of atoms using this Gibson trick, and we see that the radiation builds up in the backward direction. Here's where the first pulse goes in, and we find that the pulse is growing in the backward direction. So that's a nice, simple way to begin getting the physics. And I conclude with 2 remarks. This is the first. We find that this difference frequency physics can be realized in principle in metamaterials. In particular, if I just do ordinary positive index metamaterials, we have nonlinear optics. But if I'm looking at the situation in which the epsilon and mu are negative, then I end up running out of time and battery at the same moment. I end up getting this quasar effect, quantum amplification by superradiant emission of radiation. And there are analysis, there's some equations, there's some more, that's it.
Well, I think go ahead.
So far detuned in the experiment, what is that? That seems to really loosen the requirements on the coherence properties of the drive source.
So you're talking about the metamaterials?
No, I'm just asking that, in the calculation was probably done with, a pulsed monochromatic field, but probably that's not a requirement. Probably could you use something like a noise source, even as long as the noise bandwidth was much less than the detuning?
Very good. Yes, in fact, we do put in multi-mode fields. We look at turn-on adiabatic and sharp non-adiabatic turn-on. We do all these calculations and find that there are circumstances in which having a little noise is helpful because it then tends toward non-adiabatic Rabi kinds of results. But it's important to always keep the counter-rotating things in control.
Yeah, right.
Yeah. And what we're doing now is a series of experiments in rubidium, our favorite easy gas, using Ti-sapphire and looking at light emitted in the backward direction. And we're seeing these effects now, but of course, as is always the case, we see much more than we want. And every day is a new effect, and some days it's hard to explain. But we do have experimental electronics working for us. You say, okay, what about getting me a coupled pendulum analog to this? Because then the referees will like it. So that's what we did, and we found it could be done. And then we thought, well, hey, if I can do coupled pendulum, maybe I can do coupled resonant tank circuits. And that works too, and it works this way. You start with 2 LC circuits, megahertz and a megahertz plus 10%, okay? a low frequency difference. 10 to the 6, 10 to the 6 plus 10 to the 4. And now we drive those circuits with a field which is the low frequency, 10 to the 4 frequency difference. And when you get just the right power and just the right frequency detuning, which is the difference frequency, the two modes jump into existence. So you're generating megahertz radio frequency radiation with input, which is 1% of the frequency of the generated oscillation, LC circuit. So that's what I think really is convincing. And that experiment, little electronics undergraduate experiment, is explained in this PRX paper.
Well, now, I'm sorry, I just have to ask. So, but what's the nonlinearity in the case of the LC circuits? Here you have the two-level system nonlinearity. What's nonlinear there?
Yeah, so what we do is we put in the frequency 10 to the 4 hertz as a coupler. So we're taking the signal from these two circuits and passing it through a nonlinear coupler.
Oh.
Think triode,
Right.
okay? And this coupler then generates the necessary nonlinearity, and you modulate that coupler. It's always this modulation frequency that counts.
Okay. Okay.
Good question.
For me? Okay, is there a collective recoil? I mean, it seems if you get this huge amount of light coming out collectively in the backscattering direction, then the atoms have to recoil in the forward direction. And so for cold gas experiments, at least, that would be a huge kind of issue. So I was wondering what your thoughts or comments were on that.
Yeah, it's an interesting question. We recall that there was something called CARL, Coherent Atomic Recoil Laser. Bonifacio and others, Phil Hemmer and others were working on this back in the 80s. And it turns out that those results are not really very clear, and you probably don't need the recoil to get the experimental results that they got. It may be that they were seeing this kind of effect. And since we have a lot of collisions and a high density gas, we're looking at 10 to the 16, 10 to the 17, whereas lasing without inversion can be as low as 10 to the 9 atoms per cc. So that kind of, rigorous binding, Lamb-Dickey localization of the atom when they try to recoil is such that probably the whole mirror atomic gas configuration soaks up the recoil very nicely, and we don't have those sorts of effects.
I have extremely naive question, which probably I missed something. So let's say instead of rubidium, we're talking about our favorite non-obtainium, which known to have ideal two-level system. So everything scales with the number of atoms. So that means that however weak the drive optical frequency is, we can always scale with the number of atoms. So that it looks like you can send a single photon of infrared light and get the photon of UV light. What about energy conservation? Because we start with the atom in the ground state, if I understand correctly, so there is no energy in the atomic ensemble, or there is hidden source of energy I just missing.
So that's why I like this Gibson business, because it shows that the physics is such that I really am using 3 photons to get to the excited state. But I'm not using it in an incoherent way as would be, say, found in Bob Boyd's book. I'm doing a Glauber-esque kind of excitation in which I have classical electrons driving me into a coherent state. So it's this kind of non-incoherent, this kind of coherent excitation that gives you the right to brag for such high collection efficiency. Very important point.
So you showed this exponent, right? You showed that this kind of an instability grows exponentially. But of course, eventually something will saturate it. So is it going, in your opinion, is it going to be the recoil or depletion of the drive? What do you think will be the dominant
Yeah, it would be
mechanism?
the saturation of the drive. You're absorbing all the energy coming in from the infrared source, and you're now flattening out. And we're seeing saturation in the experiments.
But you looked into the issue of recoil, because recoil can also saturate.
I'm sorry, say again?
The recoil can also saturate this process. For example, when we first proposed superradiant amplification in the plasma, the saturation mechanism was the recoil, not the depletion. So it could you know, it's an issue that probably needs to be looked
I'd
into.
love to talk to you more about that. But what we're doing right now is just trying to simulate the experiment such that we're putting in the drive radiation and we're looking at what's coming out in the back direction. We don't see anything in the forward direction. And so right now we're just about to the point of declaring victory. But we haven't quite nailed down all the parameters yet.
So if this experiment would benefit from higher density, so why not do it, let's say, in a solid, where every single or every other or every 5 or 10 of your of embedded objects in a solid is an oscillator.
Yeah. So we would like to use a solid in the case of nonlinear metamaterials. Maybe I don't have to sweat so much. If I could just get something such that we are able to get negative index materials in a solid, that would work very well. Maybe on the other hand, what I could do is take diamond vacancies and sprinkle them all throughout the crystal and get the density up. Could be. But if I just go to the lab and build a heat pipe technology that Steve Harris and people were doing, 20 years ago, I can get 10 to the 17 atoms per cc. That's good enough, and I never have to worry about melting my crystal. So that's what we've done. That's what we're doing right now.
Doesn't that set your coherence time? But your decay rate is n gamma, so doesn't that set your coherence time as 1 over n gamma? And now aren't you down at sub-femtosecond?
Yeah, so you say that, you say, well, gee, you're going to be wiped out by the very effect that you're trying to appeal to. And so I call this the Goldilocks effect. I've got to hit just right between these parameters. And so we're doing the simulations based on, we're doing the experiments based on our simulations.
How many?
Ultimately, we're just going into the lab and throwing everything into the gas and seeing what comes out. And it looks good.
So kind of I'm a little bit worried about the lack of physical explanation for this.
Because I always like my strongest criticism of my friends in
Well, I mean, I want to elaborate further. So, and basically, kind of like what you taught me is that there are few things which matter in life, right? So, and I mean, like from the relevant things would be log sphere, optical pumping, AC Stark shift, and single photon radio frequency.
Good.
Right? So we should be able to understand if it's a real effect. We should be able to understand it in terms of this kind of basic notion. So from all of these things, I would say the one which is most relevant here is AC Stark shift.
Perfect.
Right? Because basically your far pheasant is a dominant effect. So what's the role of AC Stark shift?
Good. Thank you. So I didn't tell you about the fact that if you look for this effect in, say, hydrogen, the way we were talking about it, you're going to get a strong dynamic AC Stark shift. And this can, under certain circumstances, wipe out the experiment. On the other hand, you can compensate, in principle, for that AC Stark shift a variety of ways. And we explain some of these ways in the PhysRevX. But what we're doing in the lab right now is we're sending in light, which is meant to simulate the Gibson 3-photon excitation. So we're nearly resonant. We're sending in detuned but nearly resonant radiation, say 800, I think it's 800 nanometers, and we're looking for something at 790, okay, but in the backward direction. If you're that close, then you don't see an AC Stark shift killer. But if you go back to Gibson and you do his calculations, what he teaches you is that there's a subtle interplay between the Rydberg states and the AC Stark shift that you see with the infrared excitation. But this is an important point that Mikhail is making. You present this to some referee and he says, well, look, we've been doing nonlinear optics now for 50 years. If this is true, somebody would have seen it, right? And the answer is no, nobody ever looked. And if they did try to look and they didn't compensate for the AC Stark shift, they would never see it. Well, I went to the lab and talked to my guys who've been doing superradiance, yolk superradiance experiments for the last decade, and asked them if they ever saw anything like this, and they said, interesting enough, I don't know, we never look in the backward direction. You never gave us enough money, we always look in the forward direction.
So can this be that actually the AC Stark, the stuff which compensates AC Stark shift is the actual origin for the effect?
So he says, well, maybe one way to look at this is that the compensation for the AC Stark shift is precisely what you're doing, but in a different way of looking at it. That's a possible way to think about these experiments. But the experiment that we're doing right now doesn't have an AC Stark killer, and we do see strong radiation in the backward direction.
It's a different regime, right, from optical.
So I think it's closely related, but I think they really are separate parameters.
Well, let's thank the speaker again. And